So here I am just hopping. Well, let me do this. Just hopping on my live stream because I had an idea, just passing through my head. More like something that I would just think about. I would normally, take the dog for a walk and ponder it in the back of my head or something like that. But this time I decided to just press the stream button and thrash it out, kind of interactively. So the topic that I have in my mind right now is topic that I have on my mind is how tricky it is to think about compiler optimizations in the modern era with CPUs that are so complex and have these very important features like speculative execution, which is in the news a lot lately with some exploits, but with speculative execution and out-of-order execution. These are really, really powerful, wonderful, excellent features for the most part. I'm a big fan. I think that they're huge enablers for compiling dynamic languages effectively. But they do complicate things, and they can make it very risky, I would say. Very risky. Sorry, I had a video quality issue there. I hope it comes through. Can make it very risky to try to generalize from micro benchmarks. You can get these make it especially tricky, I would say, to know whether something that you do in a little micro benchmark is going to be representative of the impact on something larger. So I just had a specific example I wanted to think through in terms of this sealed tables feature that I've been hacking on for raptorjit. I wanted to kind of go back to where that all started and just look at it from the angle of CPU and particularly Intel CPU microarchitecture and what the implications are. So I'm just going to do that. So the program that I have is a really simple one. I have two versions. I have two loops in this little Lua script. One, it runs 1 billion times and it calls a function using the global module function syntax. And I have another one that does this with the module function cached in a local variable. So semantically, this one is doing a global hash table lookup on every trip through the loop, and this one is not. It's accessing a local variable. And I also disabled this optimization called loop optimization that would kind of make them equivalent because I'm interested in the case where code is actually emitted and running for the hash table lookup. So what I'm interested in here is to say, like, what is the runtime cost? What code do you get to do that hash table lookup, and what is the runtime cost of that? And I think it can be quite non-obvious and look at it from a few angles. Anyway, I'm going to run this now, like that. And we get, I'll expand that, we get our profiler result, which picks up the two traces as being compiled. If we take the second one first, which is the one that's accessing a local variable, line 15, and we pick that trace, we can get the IR code, intermediate representation code listing. So just on a high-level view, we've got 8 instructions of intermediate code to compile and run that loop that accesses a local variable. If we compare this to what we got on the other one, we have 19 instructions there. You see this like hash table reference with a constant key and field load out of the hash table. So there's a lot of extra instructions there. Like it's more than twice as many instructions on this IR view, which corresponds usually reasonably well to machine instructions. So it's like twice as many instructions going on. But if we look over here at the profiler report, it's counting the number of samples, which is 1 per millisecond in each of the two. So what we see is that the slow one doing the hash table lookups took 7,500 milliseconds, 7.5 seconds more or less. And the fast one that only executed half as many IR instructions, it still took like 7 seconds. So actually, even though one of them is doing twice as much work in terms of instructions executed, it's only marginally, like 10% slower than the other one. So how can this be? This is a very, very interesting question, and we're going to look at it very closely in this specific example, and then we need to also be aware that this microbenchmark is not necessarily representative of other things. But if we just look at this here in a different way, if we look at the fast one, that's the IR listing. But what about if we look at the IR graph? So this is a particular visualization of the intermediate representation that is supported in this tool that I wrote. So what we see here, for each instruction, we have a box. That's one instruction, and the lines, the edges, are showing when one instruction depends on the value of another instruction. So this add with overflow check here, it's adding two operands. The right-hand operand is the constant 1. The left-hand operand is the result of this slot load, and this conversion function here that's going from an integer to a floating point number, that depends on that takes as input the result of this add. So there's a dependency here. So these are the data dependencies between the instructions, and you can see here there's actually two different islands of instructions. So here we load something off the stack, and we compare it. We assert that it is a certain function. So this is a guard to check that our code is valid, and on this view, on the dependency view, there's no connection between these things, and this is very, very, very significant because I mean, there is a control dependency in the sense that one thing happens before the other, right? So like here we see that equal on the function. We see that the little island on the right, those instructions execute first in abstract terms, but the CPU executes things out of order. So that means it's actually free to execute either in any order and to mix them up and to do a lot of kind of creative things to try and get work done more quickly. And where speculative execution comes in is that when it does this equality test, I mean, this is going to compile into a branch. So in principle, it doesn't know that these are the next instructions they're going to run, because if this equality test fails, it'll branch somewhere else. But it's going to do branch prediction and predict that this will be the thing that runs. So it's going to be able to run this code and run this code. And the CPU is actually literally going to build this same graph that we have here. So this graph is specifically modeled on the way the CPU is going to look at this code. So with that in mind, now let us look at the other slower one that has more instructions. Okay, so this is the code that we get in that case. And this is like this again, we have two islands, two like disjoint sets of instructions. This is the one that does the real work. This is, sorry, my stream quality is awful. I'm just going to see if it's due to anything that might be under my control. I might be a little bit stuck with that, and I have to live with that. I'm terribly sorry about that. And maybe I'll put up the recording after or something. Anyway, we have two islands of instructions. This is the one that does the real work. This is the thing that we care about. This is the thing that needs to be done for our program. This is the real work, and this is all the extra stuff that the compiler is doing just to to implement the semantics of the language. This is doing loading up the globals hash table, looking up a constant key in the globals hash table, and then looking up the module and the function. This is doing a lot of extra work that is only done for testing. Excuse me. My computer's slowing down. I don't know why. Anything gobbling the CPU? Yes. Let's see if that's any better. I hope so. Yeah. We have two islands of code. This is the real work, and this is the extra work. This is the kind of busy work. And the whole idea of table sealing basically came from seeing all of this extra work and saying, my God, that is such a lot of extra work. We're doing more work just on this completely predictable sanity checks than we are on the actual program that we want to run. Wouldn't it be great if we could eliminate this? And that's the genesis of this optimization, and it has been quite successful. So with the table sealing feature, we can basically compile both of these in the same way. So we can make all of that disappear. And that sounds very good because we're only going to execute half as many instructions, but we still have this very significant thing where there doesn't seem to be actually much difference in how the program performs in practice. So this one doing twice as much work, it's only about 10% slower than the other one. So how can this be? And to think about that, we have this this picture here. This is the execution engine of a Skylake, a recent Intel Core CPU. And what actually happens here is the memory subsystem is fetching out instructions. The instructions going into the front end up here, they're getting decoded into smaller micro instructions, and they're getting fed into this execution engine that is responsible for running the program. And so then when it comes into this part, the CPU is quite literally building this graph. The CPU is working out all of the dependencies between the instructions, and then it's scheduling them so that anything that's not blocked by its dependencies can run. So all of these instructions can run in any order, and they can partly run, and everything can happen. We might do this slot load. It might need to access memory. That might be out of cache. This might take a long time to run. Meanwhile, this might all run, and it's all. There's not kind of infinite capacity here, right? So this is where the stuff happens. So on every cycle that the CPU runs, on every cycle, it can execute up to 8 of these micro operations. And these can be all mixed from all of the actual work that needs to be done. And it's more constrained than that, right? Like here, it has these 8 execution ports, which is kind of like a little core inside a core. So port 0 can do all kinds of stuff. It can do integer arithmetic, integer division, can do AES encryption, can do a lot of stuff. And some of the others are more specialized. The last one can only do address generation. This one can only do stores into memory. And so it's a complex beast. It looks a little bit like the kind of CPU Chuck Moore would invent. But anyway. What's happening in the CPU is it's built the graph here, and it is trying to use these things as effectively as it possibly can. And these can be subject to starvation. If you have a long series of instructions that all depend on each other, then there's not much potential for instruction level parallelism. So if you would have a graph that is quite tall and narrow, then that's something where everything depends on everything else, and you probably can't do things very much in parallel. And that means that you would be in some sense wasting resources here, because anytime you have a cycle where there's no addresses to generate, you can't be using that, or where there's no store to do, you can't be using that. So this is if you don't use this, it's just as bad as wasting it. So I think that's the difference between these two programs, that one executes twice as many instructions as the other. But they both run at almost the same speed, and I would say the reason is that the fast one that runs a small number of instructions is mostly leaving these resources idle, I would imagine, because there's just not enough parallel work to do for the CPU to keep itself occupied. So it's not really getting much benefit from reducing those instructions. And in contrast, the one that executes twice as many instructions, it's keeping these very well occupied. So it's actually burning through more work on each cycle. And it's not having to pay for this because like the main flow of computation is still going at the same speed, and then off to the side is also churning through all of these other guard instructions on the other little island of instructions. So there is more contention for resources here, but it's not drastically much. So it's not really that far beyond saturation on the back end here. So it's cheap. And this is so extremely context dependent. So here we have a little micro benchmark that's just a one-liner. So we could look at this and say, well, you know what, this optimization doesn't look that promising because. And we could say that the optimization doesn't look that promising because there's no at the end of the day, there's not much difference. Those guards are practically free, because modern CPUs have such wide backends, they have so much resources, and everything is out of order. And it would be very easy to make a very good sounding a case for not bothering to do the optimization and to support it with data that we have right here. Fortunately, I didn't look at it this closely. not, I didn't think of it in that way, and I actually went and did the experimental implementation of the optimization and found that it does actually seem to be beneficial on the MD5 benchmark, where we've tested it at least. So we don't actually know how broadly applicable it is, but what we've kind of seen here is that on a little program like this, there's not much benefit in eliminating the guards, but on a bigger program, well, okay, 10% is still significant actually, so I don't want to downplay that too much, but it's going to be very dependent on the context. It's going to be very dependent on how much, how close the processor is to being saturated by other things going on in the program. So everything is related, everything is contributing to the workload. So if your program in general has saturated the CPU backend, then it's going to be a big problem to introduce a whole lot of extra guards, because you already have contention. Something else is going to have to wait while those guards execute. And in contrast, if you're doing like a lot of memory accesses or something like that, and the CPU is spending a lot of time waiting and doesn't have any work to do, then it's going to be completely harmless to introduce a lot more work that doesn't add to the kind of the latency chain with the data dependencies of the main computation. If it's happening off to the side, in that case, it's not going to matter. So that's the brain dump side of it. That's just meant as a little bit of texture for how tricky it can be to think about what optimizations make sense, and whether there's actually any benefit in eliminating instructions or not, and this kind of thing. And this is actually incredibly processor dependent, right? So this can change massively from generation to generation. So this picture with the backend, this changes rapidly. So it's not very long ago you only had 6 of these units and fewer, and so Intel is always adding more of these, moving them around, changing their capabilities. This is a very dynamic picture. So what's good on one CPU is not necessarily good on another, and it's a bit of an art form to make sure that you're optimizing for current processes and future processes, and any optimizations you do that get a bit out of date, you need to kind of garbage collect. If you need to at least be aware of how closely you're targeting which processes. Anyway, it's a tricky and tough thing. And now, having done that brain dump, I just reflected that we actually have a little bit of interesting data that we could check out here based on the previous hacking that we did on the sealed tables. So we had an R up and running where we ran a benchmark comparing this sealed tables optimization, comparing with and without, and we saw that the overall performance on the MD5 on the MD5 benchmark the effect was positive. So the optimization does actually make a practical difference, which means that it's when you're measuring wall clock time, you can kind of, in some sense, measuring wall clock time on a real benchmark like MD5, that's something you can kind of put in the bank. If you make a significant improvement in the time it takes to do MD5, then that's a good thing. And that's more important, obviously, than just seeing if you profile the numbers on a micro benchmark somewhere else. But the thing that I just tweaked to now is that we have in our CSV data here, we have both. We have the wall clock time that elapsed while running a benchmark. We have the number of instructions that executed, and we have the number of cycles. So an interesting metric to look at here could be the famous instructions per cycle, and just to see as a loose approximation of how busy the CPU backend is being kept, to see whether the CPU is burning through more instructions per cycle in one version than the other, which I would just find it interesting to put a bit of texture on that, get an idea of whether both of them are kind of saturating the backend, or whether when we enabled the optimization, it reduced contention in a productive way, or we'll see what the data can tell us. But I think it's interesting anyway. So we're going to have a little bit of a dig. And what we have here is, we'll pick this most dramatic graph on the left. So we'll just take the data for where we disabled loop optimization, just because it's the most interesting. We mostly want to compare. We're also only going to look at this no locals one benchmark variant. So we're going to compare loop optimization disabled and running a benchmark that would ordinarily make a lot of global lookups if we didn't have the sealed tables feature, and then we're going to compare with and without the sealed tables. So let's do that. Let's make ourselves a little bit of space over there. I'm doing this in 720p, so I need to economize on screen space. Okay, so we have our data, and what do we want to do with that? We want to take out, we might luxuriate and actually use a file. Okay, we have our data, and we want to pipe that into, first of all, we're going to filter it, because we only want the ones where loop optimization is disabled. And okay, we have that, I think. And what else do we say? We want the benchmark. We only want the one where the benchmark is this no locals one that does a lot of global references. No local. And now the thing is that we have 100. I have an idea that I would like to plot things with, like I'd like to plot the instructions per cycle somewhere, but we have like 100 samples for cycles, and we have 100 samples for instructions. So I think we're going to boil this down to averages. Just collapse all of the rows for each variant into a summary with the average for cycles, instruction, seconds, instead of having 100 different instances. And we're going to use this Diplia. I'm calling the library Diplia. I looked up what's the official way to pronounce the library's name, and the author said pronounce it however you want. So it's therefore officially it's called Diplia, not Dplia or something like that. So what we're going to do is swap this back into our brain. We are going to want to group these. We're going to want to group these by the version and just by the version. We want to separately group the maybe we'll come back and put more data in later. Anyway, for now we're going to group them by the version, and we're gonna summarize to boil this down. So we have the version will be retained, the cycles will be the mean cycles, instructions will be the mean instructions, and seconds will be the mean seconds. Could this possibly work? No, cannot modify a grouping variable. Oh, okay, no, sorry. That one is implicit. What's the hotkey to run the whole script? Command return. And we got nothing out of that. Why not? What happened? We'll summarize. No, summarize should not have been a problem. Okay. What have we got? We're also going to have instructions per cycle. IPC is, and maybe that's all we want actually. Let's just simplify this a bit. Let's simplify it a lot. We're only going to get the IPC. Okay, so there was not very much difference in the instructions per cycle. We see we had 2.3 instructions per cycle on the sealed version, and we had slightly more at 2.5 instructions per cycle on the baseline. So, first pass at interpreting this, 2.5, 2.3 instructions per cycle, that's actually quite a bit. That's quite a high rate of execution. It corresponds with a CPU that is being kept well occupied. So, I mean, we had this picture here, but the instructions it's talking about are not these micro instructions. And digressing slightly, the CPU actually has performance counters where we can measure individually for these execution ports how well occupied they are. So I'm using instructions per cycle as a kind of a pretty rough approximation of that. But like two and a half high-level x86 instructions per cycle is pretty good. So I would say that this sounds like the CPU backend is being pretty well occupied. And then the difference is only slight, right? So if you consider, take as a baseline, take the sealed version, which is doing, it's not doing the hash table lookups, it's not doing the global lookups, this other island, it doesn't have this other big island of guard instructions that need to be executed. That's already keeping the CPU quite busy. It doesn't have a lot of excess backend resources on the CPU. It's already close to saturating the CPU backend. I'm saying, just based on the magic number 2.3 being, in my personal judgment, reasonably high. Then it makes sense that when we pull in this other, when we do the baseline one here, that does do a whole lot of global lookups. So when we switch here, we are doing, we hop over again, that's switching from this very streamlined version, more or less, to something more like this with a big island of extra instructions on the side. We don't have a lot. I mean, we were already at close to saturation, and now we're up to 2.5 instructions per cycle. So what I think is we introduced these global lookups. They took quite a bit of extra work, and there just wasn't that much spare capacity on the CPU backend. So all this extra island of instructions, it was then contending for CPU backend resources with the real work, with the real work that the program needs to do. And so the actual real work of the program was sometimes having to be blocked, and in order to run all of these other guards. So the CPU then, the first time around, the backend was all the real work is somewhere here in the reservation station, all the real work that needs to be done, and on every cycle, the backend was giving all of its resources to those bits of real work. So that was, everything was good. But then in the case with all the extra lookups, then this was a big mix in here of real work and guards supporting the global table lookups, and then they had to kind of take turns in the backend here. So well, yeah, the CPU backend is a scarce resource in some sense. A lot of optimizations need to be based on the idea that you're trying to avoid saturating this. But it doesn't if it's not saturated, if there's not really contention, then it doesn't necessarily help to reduce work and that kind of thing. So it's very hard to generalize from a micro benchmark. And we see in this case, just wrapping up, summarizing, when we looked in the profiler here in the tiny, whiny little micro benchmark, we saw that the one that does runtime hash lookups did about more than twice as many instructions to get its work done than the one that didn't do runtime hash table lookups, but it only took about 10% longer to get the work done. And this, I would say, is indicative of that benchmark having a lot of spare execution capacity on the CPU backend. It wasn't a problem. The CPU was having its execution units sitting idle quite a bit of the time, so this extra work just gave it something to do, and it wasn't detrimental in any way. Whereas when we ran it on the MD5 benchmark, I mean, the MD5 is doing a lot of extra stuff, right? It's doing a lot of calculations and a lot of arithmetic, so it kind of makes sense that there is a bit more load on the CPU backend, and that's where we saw that even in the baseline, without the extra hash table lookups, it was already quite busy. Putting the extra lookups made it even more busy, and this was reflected then in the overall performance and wall clock time. Oh, I've lost the graph. But anyway, this did translate into a real world, like it did take a longer time. The micro benchmark was only maybe a 10% difference, but on the MD5 benchmark, I think it was more like 45% or something like that. So it was a bigger deal. So so the moral is beware of generalizing from micro benchmarks, and yeah, that's the main moral. It's tricky. I'm very happy when I'm doing this work that I'm very focused on Snap as an application. So I've got tiny little micro benchmarks I can do for playing with ideas. We've got these kind of basic benchmark suites like the MD5 benchmark and that kind of thing, which is a bit more realistic. But then it's also very, very nice to have a real application with a lot of kind of like real high-level end-to-end functional benchmarks to test on, because you need to kind of be keeping the whole picture in mind. It's very easy to optimize the wrong thing. Yeah, that's my stream for now. Thanks for allowing me to brain dump that.